The thermal decomposition of but3-ene-1-ol is investigated at different temperatures. The results from the investigation are used to calculate the rate constant K at each temperature. Complete table 2 for the missing values at 573 K. So the first thing that we need to do is do 1 over 573 Kelvin. And looking at the data in the table, we want 3 significant figures. So 1.75 times 10 to the minus 3. And then we need to take the natural log of the rate constant. So we press the ln button on your calculator, you need to find that, and then type 15.6 times 10 to the minus 4. And your calculator, again, we want 3 significant figures. Mine says minus 6.463. So we want to give it to 3 significant figures. Same as the rest of the data in the table. The overall order can be deduced from a piece of information in one of the column headings in table 2. What is that piece of information, and deduce the overall order? Well, if you think about rate equations, they go rate equals K, and then you have concentration terms to some powers. And one of the things that we are often tasked with doing is working out K and finding its units. And the units you get depend on the order. So the piece of information is the units of K. Now, given that the units of K are seconds to the minus 1, and the units of rate are moles dm minus 3 seconds to the minus 1, what has to be on the bottom line for this to equal seconds to the minus 1? It needs to be one lot of concentration, so we need to get rid of that, and that just needs to be a power 1. So the overall order is only 1, in order for the units of concentration to cancel out and leave us with seconds to the minus 1. The Arrhenius equation can be written in the form shown. On the grid in figure 3, plot a graph of ln K on the y-axis against 1 over t. So this here is our mx. So our m is equal to minus EA over r, and our x is equal to 1 over t. We have to plot the values. So looking at the table of values that we had, our first value is at 1 over t of 1.81. So looking at this graph, we have to work out this scale. So 1.70, then this number must be 1.72, which makes this 1.68, times 10 to the minus 3, obviously, 1.76, 1.80. We need 1.81, which will be this line in between, and we want to go down to minus 7.68. So the little squares here are 0.05s. So 68, 75576, 76568 will be just before the minus 7.7 line. Okay, our next one is 1.78, which is the big line, and minus 7.08. Our next is the values that we filled in, so 1.75 and minus 6.46. Then we've got 1.72 and minus 5.88. And then we've got minus 5.3 with 1.69. We've plotted all our points. So the next thing we need to do is draw a line of best fit through them. So again, taking a ruler. And trying our best to equal points above and below the line if we can't get them on the line. This is just a tiny bit tricky with an electronic device because of the thickness of the line. But that looks okay within half a small square of each point. Use your graph to calculate the activation energy. Well, to do that, we need to find the gradient, because remember what we said up here, the gradient is equal to minus EA over R. So let's find some points to find the gradient. So we're going to draw a triangle onto this graph and find the gradient. So I'm going to take my ruler, if it'll let me rotate it. Rotate it vertical, find a point that I'm happy with. I think I'm going to go for this crossing the line here. And I'm going to take my ruler and rotate it horizontally and find another point. So I can draw a triangle. So here I'm going from minus 5.45. I'll just put the coordinates here, minus 5.45 and 1.70 times 10 to the minus 3. And then we've got 1.81. So this is 1.81. This would be 812, 814, 1.814 times 10 to the minus 3 and minus 7.75. So we can do the change in our y values. So minus 5.45 minus 7.75. So the difference is 2.3. And then the difference, doing it the same way, 1.7 times 10 to the minus 3 minus 1.814 times 10 to the minus 3. And that is minus 1.14 times 10 to the minus 4. So dy by dx. We had 2.3 divided by minus 1.14 times 10 to the minus 4. So 2.3 divided by, so this is minus 20,175. And they're allowing a range on the exam board mark scheme of minus 19,400 to minus 20,400. So I'm inside the range. Now that is equal to minus EA over R equals minus. So my activation energy is I'm going to take my answer and times it by minus R to get rid of the minus signs on each side. So times by 8.31, 167,657. But this would be in joules. Now my gradient was in Kelvin to the, if you look, because you did dy divided by dx, so it was just in Kelvin. So I've taken the number in joules per Kelvin per mole, so I've now got and timesed it by Kelvin, so I've now got a number in joules per mole. So to get it into kilojoules, I need to divide by 1,000. And I'm going to round up to 3 significant figures. I'm getting 168. And if you work through the numbers that they allowed on the gradient, it'd be anything between 161 and 170 for the activation energy. 2-methyl pent 4-ene-2-ol decomposes in a similar way. So what we need to do is just go back and look at that original equation. So the original equation that they gave us in the first part looked like this. It said CH2, line, double bond CH, CH2, CH2, OH. And it decomposed to an alkene, CH2 double bond CH, CH3, and a carbonyl compound HCHO. So what if we look at what they did, it looks like they've broken it here, and this bit went to make the alkene. Okay, and it's gained an extra H. So if we do the same thing, we go one across from the double bond, we break it there, and we make the alkene. It's actually the same alkene we made before. And then we take the other section, so they took the other section, which looked like a C with two H's and an OH, and they made it become a double bond instead of being broken off, so it got H, H, and a double bond. So if we do the same here, we had a C with two CH3s and an OH, and they got rid of that hydrogen and made a double bond. So our carbonyl compound is CH3, C double bond O, CH3, propanone.